welcome everybody. I hope you can hear me all right. My name is Marcel. I'm a field application engineer at the Havoc team. I'm joined here today by Oliver Strunk, who is our physics architect. And we just want to share with you a little bit, a couple of tidbits that we've encountered as we've taken our products and integrated them into Unreal Engine. And we hope that you're going to take something away from this if you're maybe trying to expose your own plugins for maybe some central tech team, or if you're a middleware company like ourselves that just wants to take the products into Unreal. And so, yeah, let's get going. So first of all, you might not be familiar with Havok. Just to give you a super quick overview, we are a middleware company for the games market. We offer 3 SDKs, and our SDKs set themselves apart because they are robust, flexible, and battle-tested in a wide variety of titles, genres, and you'll see in a second the types of franchises that use our tech. And so we have 3 SDKs. We have the Havok Physics product, which is a rigid body simulation SDK. We have Havok Navigation, which is all about dynamic pathfinding. And then we have a cloth solution, which is about character cloth, environmental cloth. And so we have 3 very different SDKs. And the challenge for us was essentially how do we bring each and every one of those into the Unreal Engine ecosystem. So traditionally, these are the types of teams and franchises that we're engaged with. We're working very closely with most of the most successful game franchises out there. Traditionally, our focus has been primarily on AAA games. And the reason for that is really that historically, our SDKs are built to be integrated into in-house and proprietary tech, which is just very, very, very common in those high-end AAA games. So that's kind of our historical customer base. And what was interesting about this was that because such a large part of our product offering needed to be pretty tightly integrated into engines, we actually worked closely with folks on that. And by doing that, we actually had a bit of influence in controlling workflows and having some influence in how our products are being integrated. What we're seeing now, however, is quite a drastic shift towards Unreal Engine as just a general engine choice across the board. We're also getting the feedback from our existing customers and new customers we talk to that they would like to continue leveraging Havok technology in the context of Unreal. And that was an obvious challenge for us to go about and solve that. But with that switch, we lose a little bit of what we're kind of used to, which is, for example, the influence on workflows. And so that presented some of the challenges as we took our SDKs into the engine. The great news, however, is, though, that Unreal Engine is really a super open and inviting ecosystem that really invites in third parties like ourselves and makes it easy for us to expose our technology in there. There's actually multiple ways to go about this. So you can really go across the whole spectrum of types of integrations into Unreal. You can go from a super low-level source engine level integration, which is actually what we've done with our physics product, all the way to the opposite end of the spectrum where you have standalone plugins that are more or less orthogonal to engine level code. And a bit of a spoiler alert here, you can already see where our products landed across the spectrum. And now we're going to go a little bit into the details about each and every one of them, what were some of the challenges we faced, and why they ended up on different ends of the spectrum. And so the first product we're going to do a bit of a deeper dive into is Havok Physics. And Oliver here is going to tell you a little bit more about what our integration looks like there.
Hey, hello, I'm Oliver. I'm writing physics engine for the last 25 years, so yeah, I'm now enjoying being here. And we want to bring Havok Physics to Unreal. And first of all, Unreal already comes with a physics engine. And basically, we want, as a goal, then basically get the best parts of Unreal Physics, and basically is what they provide, which is pretty much the workflow, and the quality and what we are providing as Havok. So we want basically to integrate our physics engine without compromises. So what Chaos Physics already gives us is basically a workflow and editor in an environment, and we want to keep that. And of course, we want to keep the performance and the quality of our Havok Physics engine, and we also want to make sure that we align with the Havok, with the Unreal architecture. I'm coming to that later, so there are some interesting details which we need to look after. So when you're now doing this Unreal integration, then basically, so I'm just repeating the slide that Marcel showed, there's two choices. You have the plugin choice or the source level integration. A plugin choice means that you bundle your code into components, basically you bundle data and code together and inject it into Unreal. But what we wanted to do, we basically just wanted to replace the chaos simulation but keep the data flow. We want to keep the data, we want to keep the properties, we want to keep the editor. And also we wanted to keep our specific components, the static mesh component, basically, which is a core part of the workflow. And for that reason, we were not able to do a plugin integration. We had to stick to a kind of an engine level integration. And that means we actually have to integrate the source code, which is at some stage a little bit kind of an extra hassle. So basically, in Havoc, for the physics integration, we are maintaining our own fork of the Unreal engine. Basically, that integration was basically done. And it has a certain maintenance cost. When basically Epic makes certain changes, we have to react to them as quickly as possible. The interfaces in Epic are stabilizing in chaos, so I think the maintenance cost is going down. And another thing which is kind of good for us is that Unreal itself is very open about the latest development. We also have a very good relationship with Unreal, so we're able to see those changes relatively early so that we kind of shield for surprises. So basically, we kind of can integrate relatively straightforward. Because we're also doing the source code integration into Unreal, that's what the game team is doing as well. We can make changes everywhere. We try to limit that, but an example would be we have an aerodynamics component in Havoc, and then we can just expose a flag in the Unreal engine and say, okay, you do a tick box, and then you have the aerodynamics component integrated as well. Obviously, our performance bottleneck somewhere, so we can fix that. The only thing is, we as a company, Havoc, it means we have to have a very long-term commitment to actually support that integration. So it's just a kind of resource on our side, but we are committed, so I think that's something we need to do ourselves. So that's kind of the logistics, and then let's look into some of the key selling points of Havoc is actually performance. So first of all, I just want to advertise performance a little bit. Just as this is a picture from Starfield. Very often I see a kind of working with the support team, and then I say, hey, I'm not seeing any physics, and the support people tell me, hey, there's 20, 30, or 30,000 bodies in the scene, and the reason is just the scenes are large. So this is a good example. So for example, you see this kind of kitchen, but it's populated with kind of these yellow objects are basically this is actually the view from our debugging tool, and the yellow objects are physics objects. And if you have kind of throw some grenades around or multiple people play together, then suddenly you need a kind of quite a decent physics engine to pull that off. Well, sadly, I couldn't show the video, but if somebody has an internet connection, you can type in Starfield and potato. Some people might have done it, but basically people went wild and tried to spawn as many potatoes or toilet papers or basketballs or melons inside Starfield. And we're all surprised by the performance that we're getting. And for me personally, it's kind of fun, because if you read the comments, there's a lot of positive energy around those comments. I can highly recommend it. It's just fun. But the thing here is about performance. What we're seeing here, because there's so much headroom on physics, you don't have to micromanage your players. So you don't have to remove the pieces immediately. You can just say, okay, just do your thing. Or we have seen other situations where people are collecting all the boxes in the entire level and putting on one file to see whether they can break the physics engine. Or the micromanagement is also important. Sometimes you want a game where people can create things. And they might actually want to create things on lower-end platforms. So you remember maybe the game Tears of the Kingdom. So we're basically aspiring that from the Havoc physics point of view, and they really want high-quality constraints, but on a very low-end platform. So that was just my advertisement talk for performance. So now we have a performant engine, and we want to create it into Unreal. So what's the trick of getting good performance? And it's kind of silly. The answer is obvious. Avoid slow code. Now, it sounds kind of obvious, but very often I'm talking to people which kind of say hardware people and say, can you optimize this in a loop? And if you look at the data, suddenly there's a hash table somewhere in the middle, or a big copy, or an n-squared problem, which takes all the CPU. So you really have to look at the actual situation before you actually can make a thing. So, okay, now we want to get good performance in Unreal, and there's a few checkboxes we have to check. For example, we have to use a memory system, you have to use a threading system, you have to integrate the code, and we want to test. So one at a time. I think memory is interesting. For example, Havoc can easily do 100,000 allocations per frame. That's going to break any kind of memory system, just right off the box. And for that reason, I think Havoc basically caches kind of high-frequency allocations, and only very low-frequency allocations go into the engine. I mean, Unreal is just an example. I mean, it's not the first engine we're integrating, so I think we have quite some experience. So basically, we're just relying on our own system to make sure we're not kind of overloading the memory system. A little bit different on threading. We're relying on threading, but Unreal threading was actually good. And the basics, and the last thing is we need to iterate. And we need to look at the data. And how do you iterate? The first thing is Unreal Insights. You know that if you work with Unreal, then basically you just put a single line in your code, and suddenly you get a nice graph in the Unreal Insights tool. We have pictures later on. We use that heavily. Good. The other thing which is very nice about Unreal, it's a C++ engine. If you're a C++ engineer, actually, who's actually C++ engineers in the audience? Okay. Then I was surprised how well standard profiling tools work. I used Very Sleepy because of its simplicity, but because there's no Python scripts in between or kind of different languages, it just worked like a charm. Super cool. And now the interesting piece is in Havoc, what we have is a tool for comparing different engines. So we can do side-by-side comparisons. For example, older versions, newer versions. And I would like to show you a side-by-side comparison. Not between Chaos and I don't want to compare Chaos here, but between Havoc inside Unreal and a kind of best case Havoc by itself. So basically, the next slide shows so think of 5,000 potatoes falling on the floor. And we are running two engines, Havoc and Havoc. One in a perfect environment, in our own benchmark environment, and the other one inside Unreal. And let me run it. Yeah, it works. So you see basically the two engines, so basically different colors. There's a slightly different behavior because of the settings are different. And sorry that the graph is at the bottom, but you see the kind of the two engines running. And you see they're pretty similar. So it means that the integration overhead in Unreal seems to be kind of okay. And if you look at the timing, so basically this runs at 20 Hertz, probably. And we're running both physics engines sequentially, and we're transporting all this stuff, and we have a renderer, and we're still getting 20 Hertz. So I think that scene is easily feasible with Havoc in a real game environment. Okay, I talked about Unreal Insights. So this is a picture of Unreal Insights with Havoc, just using 4 threads, so it's more readable. Let me see if that's my words. Yeah, okay, so basically this is one thread, this is one thread, this is one thread. And this is not Havoc, but you see that Havoc is actually kind of nicely parallelized. So basically, we get a very good thread realization, so we kind of say we are happy, right? But there's something else on the screen, and it's this thing. It says, you probably have to read it, it says Havoc sync bodies. Basically, it's getting the transform spec from physics simulation into the scene graph. And that's basically the overhead of an actor framework. And that's also a problem that Chaos is having. So Chaos already has a solution for that, kind of. And it's called geometry collections. I'm not sure whether you're familiar with that, but when you do destruction in Chaos, then basically you break things, and you get a single actor for the whole destruction. And we could hijack just that. So basically, here's a little this kind of scene. Let me just run this. So I was just using Voronoi fracture and make it 2,000 pieces, and took me about 10 seconds to set up the demo. And when you look at the graph now in Havoc, you see basically super nice multi-threading for the collision detection part. It's the left part, and then the solver part is also very nice. We have the transform sync, which is now really good. So Chaos team has done a fantastic job here. Also physics optimization kind of phonetics, I would say here this area not great. So we see basically this kind of a single-threaded and sticks out. Now let's how to debug that. And basically, for that thing, we have to leave Unreal and go into our own visual debugger. So this thing is basically a tool which we developed over the last 20 years in Havoc to basically support people. And it's pretty much similar to what you get in Unreal Insights, except that we have tons of extra physics features on top. So basically, you see the flame graph, similar. Now we can actually scrub back and forward. So that's kind of nice. But now we want to see the multi-threading problem, and then basically it's now enable the viewer. And the different colors indicate which thread is simulating which piece. So you see basically it's a scene kind of nicely split into islands, and each of that island gets simulated by a single core. And you see that there's very few islands, so if you have something like 8 cores, maybe then we should increase the number of simulation islands. But we're not going to fix it in Unreal now because I think we're kind of happy with the performance. Now let's integrate into the scheduling. So physics is very, very fundamental to gameplay. So it's actually, when you look into the tick groups, you get something like tick group pre-physics, tick group during physics, and tick group post-physics. Because if you want to move something, then you have to think, is it before physics or after physics? So before physics, you have basically animation, forces, game logic. Then you simulate, and everything moves forward, and you render at the end. Now, there's a kind of a problem with the physics engine that when a physics engine simulates, you cannot modify it. You cannot delete a body while it's actually colliding, kind of obviously. But that means if you're not clever, then the game thread has to wait. So I think the Epic team doesn't want to have that. So basically, they just got creative and invented kind of a different system. So in Epic, they actually forked the physics engine into a simulation part and a kind of game thread part. We didn't have that in Havoc. So we actually now have to create 2 worlds. Basically, we have now 2 physics worlds, and it looks like that. So normally, we have a primary world. And that's used for pre-take, for all this stuff. But when you start simulating it, we're making a copy of the primary world. And we call it secondary world, obviously. And now the game thread can use the secondary world to do raycast, to delete bodies, to change properties. And now at the end, we have to basically merge the 2 things. So sounds on picture, sounds easy, but basically one of those worlds could hold 500,000 bodies. So making a copy is not trivial. What we're doing practically is a kind of an incremental copy. So we're keeping a copy around, and the whole engine is kind of populated with dirty fields. And the same thing goes if you make changes to the secondary world, we're keeping track of all the changes. And of course, you can get conflicts. There are certain rules where we can resolve those conflicts, but once we get there, we can get this stuff out. The copy in reality takes about a few microseconds only. So I think 5 microseconds for smaller scenes or 50 microseconds for larger scenes. So it's fairly fast. Okay, so next interesting piece, I call it quality and behavior. So since we're replacing chaos comes with tons of tests which we can just use. Also, Havoc has lots of tests, obviously, so we can all use. I think we have 3,000 tests and 3,000 unit tests. They all continue to work. But for this talk, I think the interesting piece is the behavior difference. So we have seen this benchmark speed already. And in this video, I'm now comparing different physics engines. And we have a kind of circle of bodies, and we're pushing them out and see when they stop. I'm not saying what the blue one is. It's not chaos. I don't want to rank physics engines here. But you see that one physics engine produces a nice circle, where another physics engine looks like more like a Manhattan-style friction model. And in this case, it's not really a bug. It's just this physics engine has made a choice to go for a simpler model, but maybe it's faster. And for us, it's now we can use this tool to compare basically Unreal Engine with Havoc or without Havoc and see differences. And if you see a difference, we can either say we adjust the behavior of Havoc, or we just open about that to our customers in terms of communication. So I'm nearly ending the physics talk. So basically, the summary of the learnings is basically, I think we replaced chaos We got the best part of chaos, like the workflow, and we got the best part of Havoc quite successfully, with really actually out much compromises. I mean, it's the usual. It took longer than expected. The big thing is basically matching behavior, and edge cases took longer than expected. But the big learning for us is that basically we as a team have to take the Havok integration kind of seriously. And as a kind of a goodie at the end, I think some person in our team decide, okay, what can we do with Havok now in Unreal? So I think that video is a bit older, but it just shows what you can do with destruction in Unreal. The nice thing is we can use the Unreal workflow for that and just get the good performance of Havok. Something to note, I was working on destruction in the past. And to get convincing destruction, you need a relatively large number of pieces. Otherwise, it just looks silly. If you have a collapsing building, and the building collapses into 5 pieces, it's just not great. So I think in a second we will see that. So here basically is we bringing down the building. And I think the building, for my personal taste, is okay. There's quite some smaller pieces, but it's just okay. If you just make those pieces bigger, I think it will not be a convincing destruction scene anymore. And we're really, it's kind of not really pushing Havok to the limit. I think now we try to push Havok to the limit, and I think the idea is that we can collapse the whole floor. You will see in a second. And I think that's basically what Havok can do in a game. Okay, with that, I would like to finish the physics section and hand back to Marcel.
Cool. Well, thanks so much, Ollie. I'm going to focus for the rest of the talk on the 2 other products that we have. I'm not going to the level of depth that Ollie just did, and the reason for that is actually that those products are integrated more on the plug-in side of things, and so we're less tied to the underlying engine a little bit. So I want to start talking a little bit about Havok Cloth. Again, spoiler alert, we kind of end up somewhere in the middle of this integration spectrum that you've seen throughout the talk. Before I go into that, I just want to give you a little bit of an overview of what Havok Cloth is. As the name suggests, it's all about clothing simulation ranging from environmental cloth and colliding with the physics environment, as you see in the top right, to character cloth, to layering, tight-fitted cloth. There's just a broad range of use cases that we see that folks want to clothify. And so in order to enable folks to do this, what you really need that is less of an issue on the physics side is a lot of good tooling around that. And again, by working closely with so many of the top franchises that have pushed our cloth product to the limit, we have a tool that gives you a lot of control, a lot of flexibility, and supports this broad range of use cases. And so when we, again, talk to Havok Cloth users, really what we're hearing is that folks want to keep that level of control and flexibility. They don't want to give that up. Sometimes that is motivated by things like strict constraints from maybe brands and how their brand has to appear on shirts. And so there's this external drive, but then there's also just simply the artists that don't want to give up control. Users also want to reuse Havok Cloth assets and want to continue building on top of our pipeline. So we're kind of set up to be a flexible pipeline that is there to be extended upon if it's needed. And that's just another piece of feedback that we got, which ultimately led us to the decision that we actually want to draw the line for our integration between the tools and the runtime side. So what we ended up doing is we don't touch our tool. It stays as it is. We build an import into Unreal, and then we provide a full integration for the runtime side. And so when we look at Unreal, what's already there is actually an FBX import pipeline. So we thought this seems like a great match. Let's see if we can get if we can use that. What we found was that there was one caveat to that, which is if you have 2 meshes with more subsections, in this case 5, what would end up happening after the import is that for performance reasons, the FBX import pipeline would merge certain mesh sections together, which again, that's great for graphics in a rendering pipeline, but maybe you want to simulate different sections slightly differently with different cloth settings. And so that was kind of a bit of a breaking part of the FBX import pipeline, which actually meant that we now had to consider doing engine source changes to the importer to ensure that we could keep these sections as they were. But again, there was just a super positive surprise in the openness of Epic that we found, which was actually that Epic simply took that change that we had to make. So even if you're thinking about building something similar and you're kind of getting up against that wall of, oh, now I have to touch engine source code, there's actually a good chance that Epic will be open and you might be able to merge your change into the engine, which enables you to remain a standalone plugin if that's something you prefer. So yeah, that was just really great, and it's something that we actually didn't necessarily expect from the get-go. And so what that allowed us to do was just simply use the out-of-the-box FBX import that we had, so no engine source level changes. And then we could build our own importer on top that sits inside of a plugin that imports proprietary Havok cloth data. After the import, we merged it together, and then we have our asset running in-game. And so this is what the integration ends up looking like in terms of distribution. So it's two parts. It's a standalone plugin that contains the runtime and the import. And then there's the Havok cloth setup tool, which is a standalone tool that we ship alongside that. Again, this was a non-trivial trade-off for us to make. The alternative would have been to try and snap to Chaos Cloth workflows, but ultimately, we just found that we couldn't maintain the level of control that our tool provides, and that's why we went down this road. There are downsides to this, which is, for example, on the workflow side, this means that users have to leave the Unreal Engine editor to author their cloth. So there's a bit of a downside to that, but on the plus, again, we keep the level of control and flexibility. And we actually took some steps to kind of mitigate at least a little bit the slightly longer iteration loop. So for example, one thing that we ship in our integration is an automatic conversion tool that just kind of gets you from a Chaos Cloth asset to a Havok Cloth asset rather quickly, just so you have a bit of an easier time learning the new tool chain that you use with Havok Cloth. And so again, this was just a small sort of, I found that kind of an interesting choice because tooling is such a big part of cloth that I wanted to share with you all. I do want to spend a bit more time also on the Havok Navigation product. And again, if we look at the spectrum, this actually sits all the way to the right, which means it's a full standalone plugin. There's no engine source changes, and all we ship here is the plugin on its own. So again, just to give you a little bit of an overview of what navigation is, as the name suggests, we're all about 2D nav data generation, 3D nav data generation, and then perform dynamic pathfinding on top of that and support things like a dynamically changing world and moving platforms and all of that stuff. And it's actually those features that are around the general theme of dynamic worlds that we're hearing is where folks get a lot of the value out of Havok Navigation. So we wanted to make sure that features like traversal analysis, which I'm going to show in a second, 3D navigation, and support for things like moving platforms, we wanted to ensure that we don't lose that. So the goal essentially was we had a pretty well-defined solution in box that we wanted to replace, essentially get to feature parity with that, but then build on top of that and expose our own sort of more Havok unique feature sets. So that was the goal. The challenges that I'm going to talk about a little bit is, first of all, how do we go about matching existing workflows when we're a standalone plugin? Then how did we get to feature parity? And then finally, I'm going to pick a couple of those more unique features and show a little bit what we ran up against when we tried to integrate those. So first challenge around workflows. Again, I've made the point at the start, but like one big draw to Unreal is just the way the workflows work for people. People are used to them at this point. People know what to expect, and that's something we don't want to break. We didn't want to break that with physics. We didn't want to break that with cloth, and we definitely don't want to break that with navigation either. So one sort of general philosophy that we've decided to pursue here is we want to align as much as possible to the high-level concepts of the existing Unreal Engine workflows. That was a decision we had to make pretty early on, but this really paid off. So if you are thinking about maybe replacing parts of Unreal, if you have the ability to snap to a workflow that's already there, it's most likely the right choice to pursue. So just to give you an example of what I mean by snapping to a workflow, what you see on the screenshot here is the inbox navigation solution, which is the slightly darker green mesh, and then the Havok Navigation nav mesh on the right. The way this works, I'm sure most of you are familiar with this. What you do is you drag a nav mesh bounce volume actor into your scene, resize it, and anything that's contained with that will have nav data generated for it. That matches pretty well with how the Havok SDK works as well, and so that's exactly what we essentially mimicked. So we ship in our integration a Havok AI nav mesh bounce volume. It works exactly the same way, and this is super helpful for things like project migrations. People already are familiar intuitively with a workflow they know of. All they have to think about is, okay, there's maybe a prefix in front of the actor that I have to drag into my scene. So that was one part. The second part is around getting to feature parity. We actually thought that was going to be a big challenge because there's just the feature set is just really broad, and there's a lot of systems that are touched by navigation. But what we ended up finding is actually that it was much easier than we expected. We provide similar blueprint nodes, super easy to extend that. We integrate into the behavior tree. It was super easy to do that. Just override a class and you're good to go. Things like gameplay tasks are super easy to extend. And to Ollie's point, this all means then that it fits nicely into the existing tools for debugging, performance, stats, and all of that. And then support for the Unreal character system, things like AI controllers, path following components. That was all actually really easy to extend, including the EQS system. All we do is simply provide our own implementations of the queries that are there. And so the third challenge was more about exposing the Havok-specific features where there isn't a workflow that we can snap to. This is one example I wanted to show, which is the traversal analysis feature, which I've mentioned before was kind of crucial that we make sure that gets exposed. What that does is it automatically generates traversal links between nav mesh cells based off of character capabilities. So for example, you might have a jump between two nav mesh faces. This system just generates those jump nodes automatically. That actually fit pretty nicely with the nav mesh generation settings themselves. So really all this came down to was adding a submenu to nav mesh generation settings, and that was it. So that was surprisingly easy. What was a bit more challenging for us to do was getting our nav mesh solution a nav volume solution to work with the world partitioning system. That's something we wanted to support. And so what we ended up doing there is we opted for a grid-based nav data generation system. So you generate a grid, and within those individual grid cells, you get your nav meshes, and neighboring grid cells need to then be merged at runtime. So what we've done there is we've pursued an actor-based approach. The really nice piece about that is that it just automatically then works within the world partitioning system. So we can do things like store nav mesh grid cells inside of level instances without actually doing any additional work. However, there are other challenges that come with large worlds. And I want to focus a little bit on the authoring side more than the runtime side. So for example, even on the editor side, not all grid cells will be available. And so if you're working in the editor, you kind of have to handpick which cells do you want to load in. And then there's also the problem of how do you actually stitch individual nav mesh sections together as they're being loaded in. That's actually a feature that our SDK just supports out of the box. So that was fairly trivial to do. So we could just hook that up and it would just work. Where it gets a bit more complicated are areas where we're dealing with sort of cross-cell information that we need to be aware of. So for example, we have this feature called global region pruning, where you can remove pieces of nav mesh that you don't care about. Typically that's size-based, so things like nav data on top of a car roof is something that usually you don't care about, so you just want to prune that out. Or in the example that you see in the screenshot, maybe rooftops of buildings that the character can never reach. But if we think about that problem, it can actually quickly become non-trivial. So what I'm trying to illustrate with this graphic is a piece of geometry in blue that spans multiple nav mesh cells, in this case 3. If we only have the information of the left one available, We might prune out this region because we think it's below a certain area threshold, but we would be wrong in doing that. So what we actually have to do, both on the runtime side and during the editing part, is we have to make sure that all the relevant cells are actually loaded in and available. Similarly, with the traversal analysis feature that I talked about, we might have a single loaded cell, and we might have a jump within that cell. That part is easy. But jumps can also cross into other neighboring cells, or maybe even you have a customized traversal, like a teleport or something like that, that could reach a cell completely on the opposite end of the map, for instance. And so that was something that we hadn't originally really thought about and kind of sort of discovered as we went along and had part of our integration already done. But again, there was actually great news at the end of this, which is that there is, again, infrastructure available for this within the context of Unreal. In this case, this is called a loader adapter interface. If you're maybe exposing a similar solution where you have to worry about, which pieces of information are available at editing time, not just at runtime, that might be an interesting interface to take a look at. It essentially does exactly what we need under the hood. You can provide your own implementations. We've done that for all the operations that cross grid cells. So for example, we have an implementation for the global region system that just automatically, transparently, under the hood, loads cells that it needs to make the call on whether or not to call a region out. And similarly for the traversal analysis system. And so what we ended up with was, again, this is kind of summarizing what we've talked about. We were able to deliver our navigation solution fully as a standalone plugin, which is quite valuable for folks because it's easy to pick up. And yeah, the reason I keep showing this integration spectrum is that this is actually a really crucial decision that you have to think about from day one on. Are you trying to avoid engine source changes? Are you striving to become a pure standalone plugin? Because the consequences of that can be quite wide-ranging in terms of how you deliver the plugin, how you deliver. Do you need a full fork of the engine source? And also, how well can you actually snap to the workflows if you decide to go with a standalone plugin approach? So I want to leave you with one final slide, which is essentially a bit of a checklist. So what we've done is we've surveyed engineers within Havoc and outside of Havoc as well, and just asked them, look, what were sort of the maybe the learnings that people don't think of when they start building plugins for Unreal or integrating into Unreal? And we actually got a quite wide range of answers. But the general themes were around early investments in just the infrastructure that is there in Unreal already. Things like Unreal Insights, the stats system, memory tracking, integrating into the viewport for debug viewing, actually something that's really important and something that is very easy to put off until later on. But usually this investment into these sort of core pieces pays off, and it's worth doing. The second point is just leveraging all the available documentation that is there. There's obviously the reference documentation, which is great, but typically you should go in with the expectation that you have to go a little bit beyond that, like you have to step into code a bit more. Part of that is simply because Unreal Engine is constantly changing. So it's just something to be aware of and to not forget to just lean on one source over the other. And then finally, on the testing side, don't forget to leverage tests you already have. There's a good chance you can either bring them into Unreal or maybe connect them to Unreal in a way that Oliver showed for the physics side. And then also leverage the automation system that is within the engine already. And yeah, I'm just going to leave this slide up in case folks find it interesting. But with that, I want to end it here and maybe open the floor up in case there are any questions from folks.